recording and simply say, so we're back, and we just simply watched the linked list portion of the crash course data structures video. So you should check that out. And I don't record that simply for, because I just feel like that's not something I should do. But we're going to talk about linked lists. So linked lists are these special kinds of lists. They're a different kind of lists. And this is your greatest weapon with understanding linked lists, which is a writing utensil. This is the part of the class where basically if you draw or write on a notebook, this is going to be really good for you. Or if you just need to grab a dry erase marker and write on a window or a whiteboard or something. So we're going to be going over singly linked lists. They aren't going to be circular. So here's pretty much the way it's going to work. We're going to learn singly linked lists. Then we're going to move up to doubly linked lists, which is how stuff is usually implemented. And then for your homework that you'll do, not this week, but that's going to be assigned to you the week after, where I'm going to say you know enough about linked lists to work on them. You're going to be programming a circular linked list that happens to be singly linked. We'll get into what those terms mean, but you're going to write that, and then on your exam, you'll focus on solving problems with mostly singly linked lists and array lists, and possibly there might be a question or two about doubly linked lists. I'm going to see how much I want to change my exam, because my exams have been fairly static for this first exam. And we're going to see how well I can change that. So singly linked lists are basically, the idea here is that we want to add and remove at arbitrary locations. And primarily, we want to add and remove stuff into the list from the beginning and the end most of the time. Okay. With the array list, we saw that it was pretty terrible for it to add and remove stuff compared to the speed which you could get stuff. Right? You could get something out of an array list very quickly. You could change something in an array list very quickly, but you can't add and remove from that array list very quickly unless you're working on the end and if you don't happen to reallocate. Right? So linked lists can add or remove elements in a known location in constant time. That known location is important. That's typically the head of the linked list, as we call it, which is the beginning, or at the tail, the end of the linked list. The linked list, instead of an index, we basically, instead of putting them basically together in memory, as we saw with the video, they are in just random points in memory, and each one tells you where to find the next one. Linked lists are kind of like a scavenger hunt, where basically, you go to a location, you find the node, and each note contains the location of the next portion of the scavenger hunt, right? So the scavenger hunt directs you to an item, typically in the scavenger hunt, right? And that item also happens to be bundled with the directions to find the next item, and so on and so forth. So this is a scavenger hunt through your computer, but fortunately, it's not too hard for your computer to jump from one location to another. Okay. So the first thing we need to understand is what we use to build these things, which we kind of almost built this earlier when we did the box that holds something. Nodes hold a data item and one or more link. So a link is so this is going to look a bit weird, but when we actually program it, but it's easier if we start with the diagram. The node points to another piece of data. Specifically points to the next node in the list. So the node holds the data and the next item in the list. I'll get into the second, but basically here's the way they write their list, which is a private static class, which means that the static keyword means that it's not going to be outside of the current class it's in. So basically, it's bundled inside the class inside of the linked list class. Hence, it being a private class because nobody else can see it. And it's a static class, meaning it's just not going to exist outside. So it's a nested class. It's nested inside the actual class. Now, I prefer to write mine outside, but putting it inside seems like good practice for here. But this is the way a linked list kind of looks like. A linked list just simply contains a reference to the first node in the list called the head. Okay. We contain a reference to the node as a single reference. It stores the location of the first node in the list. And that first node holds a holds a reference to the data that it's storing and the next item. And that next item has data and the next item in the list. Then so the next one has data and then the next item in the list, and this one has more data, and its next item is null. So there's nothing that follows after it, right? So the size of the list is 4 because there's 4 items, there's 4 nodes here, each of which has 1 item. That makes sense to everybody? I want to make sure that I didn't lose anybody. Now generally it's we can draw these just a bit easier. Normally I don't draw all the stuff in the linked list. Typically what we do is that we draw it kind of like this, right? I will draw it by saying that basically this is the head, and the head contains Tom. Next one has, next one is, and the nice thing about this is that at least with linked lists, is that I can put these pointers wherever I want, and it's still easy to follow. So Tom, Dick, Harry, and that's just an abridged way that I'll often do it. But remember that basically that the node contains a pointer that stores the location of its data, and it has a pointer that stores the location of the next node in the list, right? And this is going to be crucially important when we actually work with them and write the methods for them, because we're going to build these things from scratch, just like we did with the array list. Okay. Oh, that was interesting. Okay. So connecting these nodes, right? So you could build an array list like this, where we've got a node that holds a string called Tom, a node that holds a string called Dick, Harry, and Sam. And we can say that Tom.next, that's going to point to Dick, Dick.next is going to point to Harry, Harry.next is going to point to Sam. Okay? So those will all point to each other. But what we need to remember is that basically that the way this works, okay? The way this works is we got to remember how Java does assignment statements, right? Sam is an expression, believe it or not, right? It's an expression. And what we do is we evaluate the expression. And what Sam gets evaluated to is a memory location, right? So then there's the memory location we have a memory location on the right side of the assignment operator. And that gets stored in the variable on the left. It gets stored in the .next variable of Harry, right? So Sam gets stored in Harry.next. The memory location of Sam is stored in Harry.next. Now you might be wondering why I just basically repeated that a whole bunch of times. And the reason is because it's important to understanding how that works. Dick gets stored in Tom.next. So, so this will connect things just like we did, but Sam would follow Harry. Generally, though, we don't have an individual reference to each node in there, right? Instead, we just have a single reference to the first thing in the list called the head. And then we just add items. Then we need to just attach we attach items as we need. So this is where I'm going to diverge from the slides because they use a bunch of methods, and I find it makes it confusing a bit because the way they write it, I want to they write it differently, and the way I like to write it makes sure we don't have to deal with any exceptions. And I find the best way to start learning linked lists is to dive right into the mess of writing them. So we're going to start out pretty easy. So I'm going to create a new class. It's going to be in the package for me, linked list evening. Okay. And we're going to build ourselves a linked list. Okay. Now it's going to be a linked list of stuff, right? So we're going to use generics there. Okay. And the other thing we mentioned is that these are going to have a node, right? Just go ahead and create a private static class node. And I need the node E. So this means that basically we've got a node here. Now, if you need to, you can make this a public class in a different file if you feel more comfortable doing that. But this enables me to make all this stuff private and work with it pretty easily. So nodes look like this. So just right now, don't focus on the outer layer at all. Just focus on the inner layer right now. This private static class, treat it as its own thing. The node has it's very simple. It has only a couple lines to it. It doesn't even have any functions. It just has two variables, a private E item, okay, it's of type E, and a private node E next. Now this is why that's why I wanted to watch the video first, and why I wanted to go through the slides a bit first before we start coding. Because when a lot of students see this, they're like, so this is a node inside of a node. It's like a, Russian nesting doll kind of situation where basically it holds, each one holds the next one. And that's not the way to view it. You don't view it as a Russian nesting doll, right? Where basically you open the shell of the outer doll and inside is another doll. No, what it's saying is that it's contained, right? Just like this is the memory location of the item that we care about. This is the memory location of the next item in the list. Does that make sense? This is the memory location of the next item in the list. Okay? And we're only going to build one constructor to make it pretty easy, which is public node, and I'm not even going to bother setting that up. Which is what we're going to do is, what is the problem? Remove item, keep item. Assignments with side effects. Don't know what it's getting at. This dot item is equal to item. What does it want there? Don't know why it wants me to do that. Regardless, that's basically all the node's going to look like. It's got an item, a next, and then it takes in the constructor that takes in an item and sets it up. Now, what is the next node in the list? Sorry, what is the next in this case going to be? Null, right? By default, if I don't provide anything, this is what would happen. This dot next is equal to null. So it doesn't point to anything. So when you're programming, the potential problem you have here is null pointer exceptions galore. But I'm going to do my best to basically program this in such a way that you don't have to worry about null pointer exceptions. Okay, now the instance variables for a linked list, on the other hand, are fairly straightforward. The first thing is a node E head, which is the first item in the list. We only really keep the linked list only really keeps track of the first item in the list. Okay? Why does it want remove head, keep assignments with side effects? Right. So we have an item that's the head of the linked list, and then also we'll want to keep track of the size of the linked list. So private int size. Okay? And then we'll create a constructor for it where basically we say public linked list takes in nothing, and we'll say that this dot size is equal to 0, and that, okay. Actually, do I need this over here? Yes, I do. Awesome. So we've got our linked list set. So we've got basically the linked list set up over here. So the question is, how do we add stuff to the linked list, right? And it's actually fairly straightforward for a singly linked list, which is that essentially there's only 3 cases for it's going to look complicated, but what it comes down to is that there's 3 cases when we add stuff to a linked list. The first thing is that when we add something, the first case is that it could be out of bounds. Okay, And that's pretty easy to handle. If we're going to handle it the same way we tried to add something out of bounds to a array list. We try to add something to a linked list as out of bounds, we just throw an exception. So that's fairly straightforward. Second thing is that if we're trying to add a new item to the front of the list, a new head of the list, right? In which case we'll have to update head. And then the third thing is that if we're trying to add anywhere else. Now later on we'll maybe add a tail variable, but we don't really need one right now. And I'm not going to overcomplicate things by adding a tail variable because then we'd have to add another condition. Right now I want to keep it 3 because that's pretty simple. Keep it at 3 conditions, that is. So example of what adding to the head looks like, okay? We've got a singly linked list that takes in a node. And that's composed of basically singly linked list. Its head points to this first node, Tom, and then the second node, Dick. Okay. Say we want to add Anne to the list. So we want to add Anne to the list, and we want her to be the first item in the list. Instead, what we do, so what we do in this case is that we set up so that Anne points to the first item in the list. And then we update the head of the list to be Anne. Now, it's important the steps that we do this in the proper order. Okay, and the rule of thumb to always follow is we want to modify we want to set up the thing that we're adding first. So set up the thing that we're adding first, then modify the variables in the list that already exist. And I'll show you why that is. Because if you haven't learned about how garbage collection works in Java, you're about to learn how it works. Okay. So we've got the head of linked list over here. Tom's got next is Dick. Okay. So now, suppose we're in that situation where we want to add, we create a new node Anne, and we want to add this item Anne to the list. First thing we do is we throw Anne into a node so that it can actually be stored in the list, because the list is a bunch of nodes pointing to each other. So that steps make sense. Now, the first thing some students, their first instinct, or at least when you're first programming this, your instinct might be, okay, since Anne is going to be the new head of the list, I'll just simply say, first step, Anne is equal to the new head. Or sorry, head is equal to Anne. We get into a problem if we don't do it in the proper order, which is what we've just done here. Which is that, okay, the linked list, another way to think about this is that we have this length. We have this head variable, right? Which was pointing over here, right? And now we've got a head variable now that we tell to point to Anne, okay? And we didn't attach Anne to anything else in the list. Now the problem is that basically if we want to get any of those other things, we can't anymore. We have no way to access them, right? The way we were accessing them was through head. Head is now gone. Or sorry, head is now pointing to Anne, so I can't get the Tom anymore. But it gets actually worse in Java because, well, in C, this would be a memory leak, where basically we just have a bunch of memory just used up that's floating around useless. In Java, though, the story continues, which is that basically Java keeps track of the number of things that reference a particular variable. Basically, how many times a particular block of memory is being referenced, like stored in one variable or another. Well, nothing is storing Tom anymore, right? Dick is being stored by one thing, which is Tom's.next, right? But Tom isn't being stored by anything. So that means that nobody's using it. So in comes the garbage collector and eats up Tom. Okay? And then we look at Dick, and Dick has nothing pointing to it anymore. So the garbage collector takes care of Dick. And then basically this will continue ad infinitum throughout the entire list. And basically your entire list will get deleted if you forget to set up your variables correctly in the right way. So instead, how could we possibly, avoid this catastrophe? So by doing things in the right order, which is first we want to connect our new node to the list, and then we adjust the existing list to accommodate for it. Okay? So when we create a new item, Tom, right? So we wanted to add and to this list, and it was initially our configuration was this, right? So first thing we want to do is we want to add and to the list. So and we could put her on a node, and then we connect her to the head, right? We have her point to Tom because once she becomes the head of the list, Tom should be the second thing on the list. Make sense? So then so now that she's actually attached to the list and we aren't going to lose anything, we go ahead and say that the head should now be pointing to Anne. Okay? Or another way to put that is that we just mark Anne as the head, which is the way I prefer to do it. I label Anne as the head of the list. That makes sense to everybody? And that's what happened. Was that the tire?
No, that was my shoe.
Sorry. So anyway, continuing on, Anne is now the head of the list. Tom, and followed by Tom, followed by Dick. Okay. So that's fairly straightforward. So let's go ahead and start by implementing this with as much as we can. So the first thing we want to do is write a public. Remember we have two add methods here. Remember the first one, and we're going to work on basically the public void add int index, right? So we want this to be the 0th thing in the list, first thing, second thing, so on and so forth. And we're going to be adding e item into the list. So again, the first thing we need to check is, are we out of bounds, right? So, and again, we can just use the same thing we did for array lists, which is if the index is less than size, right? That's out of bounds. Or the index is greater than the size, right? Because we can add to the actual size as an index. So that's why we aren't going to do greater than or equal to. We can add to the actual size to add to the end of the linked list. Then in that case, we are going to throw new array, we're going to go with not array because there's nothing to do with arrays in here. So index out of bounds exception. You can just do exception-y on a test or runtime exception on a test, and that's fine. Okay. Otherwise, there's two other conditions here right now for adding to the list. Okay. If index is equal to 0, so that's basically the first thing, which is the situation we're describing right here, right now, which is that if we are adding it to the list, if we're adding a new head to the list, right, we're adding it to a new first thing in the list. That's our first condition. Yes.
Based off your if statement, why don't we just say index not equal to size?
Because I might want to add more later, and it also I'm pairing it up against.
Because the way that it's currently based will always throw it if it's only
index. If index is less than size or index is greater than size. Oh, when did I say 0? Okay, 0. I don't know why I was saying size over there. Index is less than. This is the issue with live coding. Sometimes you make mistakes. Let my mouth get ahead of me. So, but good catch on that. Everyone else, how could you let me do that? Okay, so index is equal to 0. So the objective here is to make coding this up as simple as possible, so we don't have to worry about like the normal null pointer exceptions and worry about like other conditions. I just like keeping it pretty simple. So if we're adding, so before we start filling this up, let's just remember the last few things, which is that if we're adding something to the list, we definitely want to remember to increment the size. Okay, and the other thing over here is that we want to say node e. Let's go with not new node, but we'll go with let's see, I want to say new. I would love to put new, but new is a new keyword, so we'll just go with node over here, right? Actually, I'll go with temp. Temp. Let's go with temporary because we're creating a temporary node. We're not going to really give it a name. Temp is equal to new node that takes in the item. Okay. So we've stored the item in a node. So again, the first thing we need to do is attach the first thing we want to do is attach the new node we just created to the linked list. We want to attach it to the head of the list, right? So remember the proper order for this. It's not this. It's not head.next equal to or temp. You know, a lot of times I see flailing. You actually got to think about it. There's an equal sign over here, what we need to put, right? So the first thing is on the right is the memory location that we're storing, right? So we're going to store head. Where are we going to store head? We're going to store head in temps.next variable. Another way to look at that is that we're attaching temp to head, right? We're connecting temp to head using the .next variable, right? That's another way to look at it. Just look at whatever paradigm you need, but the real way it's working is that we're taking the memory location of head and storing it in temp.next, okay? So that will add it to the front of the list. No problems, okay? The next thing we need to do is store, is that we need to basically make sure that head is, that temp becomes the new head. So we don't write temp is equal to head, because if we did, that basically would mean that what we're doing is that we're storing the memory location of head in temp, and now temp and head would actually be the same variable. Specifically, they'd both be, temp would just be an alias of head now. Instead, we say we're going to store inside head the memory location of temp, right? You take the memory location on the right and you store it on the left. So you got to think through this and understand the way that these assignment statements work. Because it's all abstract now. It's all very abstract now. So the way, again, so let's go ahead and rewrite this. So, and here I'm just going to get even more abstract. Because really, if you haven't figured it out, the only thing I really care about in this situation is the head. So I'm just going to label it head, right? That's the only one that we really care about. Okay? We create this node called temp over here, and there could be, as many nodes as we want after here. Okay? So temp, so the first line says temp.next is equal to head. So we attach temp to head. Or the way that I think about it is that we take the memory location of head and store it in temps.next variable. So we drop this arrow over here. And then we say head is equal to temp. So we take the memory location of temp and store it in head. So we move this label over here, right? So if you want to, and I typically ask a 5-point extra credit question on the exam, which I give you a function that's basically which has a bunch of variables and a linked list, and I have you work through it. And maybe a couple of students get it right each year or each semester. But the way to do this is to go through this code and these kind of code and draw it out. That's the only way I've ever seen it solved. So temp head. So now temp is head. And I don't just do that for fun. I do this I actually draw this to double check my code to make sure it's working the way I want. I need it to. So let's go ahead and test this, as a matter of fact. Okay. Okay. So public static void main string args linked list of integers. List is equal to a new linked list of integer. Okay. List.add to index 0, let's go ahead and add 1 to index 0, and then we're going to add 0 to index 0, which of course, if we then go system.out.println list. So the first thing I'm going to, obviously this isn't going to do anything because I don't have a toString method, but for right now, this will let me know at least if it blows up in my face. Okay, so it's not blowing up in my face, so that's the first good sign. Okay, so now we need to actually go ahead and figure out how to print out this darn thing. Okay, so let's go ahead and figure out how to write that. Public string to string. Now the very interesting thing is I can go through this list without actually needing to know what the size of the list is. Normally I would have to write a loop, a for loop, but I can actually do this with a while loop, which I'll do right over here. Output. Actually, string builder. What is this string builder thing? Well, and if you can kind of guess by the name that we use it to build strings. Okay. So one thing you may not have learned is that, hold on, let me just declare it, new string builder. So one thing that you may have already learned is string concatenation, right? Where basically you can do plus with one string, you can do A plus B and you get AB, right? Well, what they don't tell you is that that plus operation, the concatenation operation in Java is actually pretty expensive computationally. And the string builder is just a more efficient way to do that. So this will make it so that basically when we print a string, it will go very quick. What we're going to do is that we're going to just glue all the pieces together when we need to. So first thing we need to do is just do output dot, and the way you add stuff to it is append it. We're going to append, since this is a list, we're going to put a bracket to begin it, and then we're going to put a bracket to end it, right? And then what we do is that we're going to iterate through the list. We're going to go through the list one at a time without having to use anything at all to basically get our way there. Sorry, any for loop without using the size. What we're going to do is that we're going to say that we're going to create a node, kind of like that called current. And what current is going to be like, it's going to kind of like be our finger. Basically, we're going to use our finger over here, and we're just going to follow, the nodes until we get to the very end. So node current is equal to the head. So right now, current points to head. Current is the memory location. Current is storing the memory location of head. Now, if I were to say, and here's where I hope. So I'm going to just pause here once I write this line, and somebody just scream if you need me to stop, because this is where we start losing students. Okay. So here is the next line, or the line I'm going to use in the while loop rather. Current is equal to current.next. Okay. So remember the way this works. We take the memory location on the right, and we store it in the left, right? Much how you use I is equal to where, remember how basically you would have to do I is equal to I plus 1, where we'd take the variable, use the data from it, increment it, and store it in here. Similar thing is going on over here. We're saying take the memory location that's stored in current.next and make current and store it in current. So if you see basically these two lines in isolation, right? In isolation, then with this list, what would happen is that we'd say, okay, currently points to head. Or better way to do it is maybe we'll just draw a little index over here, a little box over here. Current initially points to head. And let's make sure that I'm catching this. Current points to head, right? And then when we say current is equal to current.next, well, what we want to store in here is current.next. Right? This thing over here. That pointer over there. That makes that memory location over there. That makes sense? Did I lose anybody yet? Okay. So which part?
Could you just say that again?
Do it again. No problem. Okay. So right now, basically, let's go ahead and add some labels to this, because that makes this actually a whole lot more appealing than what I had. Because remember, I was dealing with a simplified thing. So this node, we'll say his data, we'll put the data on top and then his pointer on the bottom, and then the node on the bottom. So let's go with who is his data, okay? And then we're gonna do, and then his memory location is, let's go with, I'll put the memory locations up here. 0x AB, okay? That's his memory location. 0x 2b. 0x 2 1. And then over here, 0x 2 2, right? So his next is gonna, I'm gonna say his next is 0x 2b, bar, baz, and whoop. Okay. 1. And his memory location is a null. So it makes sense how everybody's got an arrow to his next, right? Okay. So what I was doing is that so this is the head of the list. And when I label it like this, what I really say is that I've got a memory location up here, labeled head, right? And it's storing 0x2b up here, right? And so what I've done is that I've created another variable over here called current. Okay? And we call this, and right now when we create it, we say that in our code right over here, we say that current is equal to head. Okay, so what we're going to do is that we are going to take the memory location in head, right, and store it into current. Let me go back to the, take the memory location in head, store it in current. And what I've been doing is I've just been simply drawing arrows, because even though that makes it messier with all the text, we see. Yes?
Shouldn't head be storing OX?
AB. Getting sloppy right now. Okay, AB, my bad. Yes, AB. Good. You caught my obviously intentional error. That's my story, and I'm sticking to it. And I'll hire lawyers if I have to. So head and current to AB. So basically, they point to the same node, right? We took the memory location in head, which was AB, and we stored it in current, right? Yes.
So it just takes the whole node and puts it into current.
Takes the memory location of the node, right? We're
Okay.
storing memory locations. So here, when I say current is equal to current.next, what this line does is that it says, okay, what is current pointing to? So first I have to figure out this line over here. We ignore this this one over here. We ignore this right over now. We have to evaluate this. And what does this line point to? We have current. Which is this node over here. His .next is 0x2b. Okay, that's the memory location, right? So we resolved this memory location. It's 0x2b. So we're going to take 0x2b and store it in current. Does that make sense?
Wait, doesn't it point to 0xAB?
It points, so 0xAB is current. 2b is current.next,
Oh,
right? So current.next, so 0xAB's next is 0x2b. That makes sense? So we're going to take that and we're going to store it in current. So now current will be 0x2b. And now if we see this line again, current is equal to current.next. We'll say, okay, what is current? It's 0x2b. What is 0x2b's dot next? It's 0x21. So we'll go ahead and update this with 0x21 and point it to here. Make sense? Okay, so that's what that one line will do. Okay, so now what we can do is, since we've figured out that trick, that we can update and go to the next node. This simply says, let's go to the next node in the list. I'm going to move my finger along and then to the next node of the list. What this will allow me to do is I can set something up like this. While current dot next is not equal to null. So while the next thing in the list isn't null, I can say current is equal to current.next. So the first thing that I can do is I can say, let's take output, and we're going to append what's currently in current dot data, or current.item. So we're going to take the item, and we're going to take the information that's currently at item and add it to the string builder, which means that all we're doing is that we're just taking the data and turning it into a string. And then we go to the next item. And then we just keep doing that until we get to the last item. Okay? And since we're adding this to there, we might want to, space it out. And then finally we get to the last item. We'll say current plus Now let's go ahead and run this again and see if it blows up. Oh, 0 linked list. Oh, current dot. So now we've got 0, 1, which are the items in the list. Let's go ahead and add more items to the beginning of the list. Let's add -12 and 5. Right? So let's just go through let's go ahead and walk through this again, through what we have over here. Okay, so now what you'll notice is that a nice thing about what I've come up with here is that there wasn't really anything special we had to write if the list was empty. That was pretty cool, because let's go back to our code to my code for a second. If the list is empty, and I want to add, so let's say I'm adding an item to index 0 and the list is empty. So is 0 less than 0? No. Is 0 greater than the size of the list, which is 0? No. So it's not an exception. So we create a new node, which we label temp. Okay? If the index is equal to 0, we say temp.next is equal to head. So that says we're going to take what's inside the list. So we're going to take this, we're going to say temp.next is equal to head, which is saying that we're going to point temp's pointer to whatever head is. Which, if the list is empty, it's pointing it out to nowhere, right? It's going to point it to nothing. That's a valid operation, setting something to null. And then we say head, which is currently null, is equal to temp. So we say we're going to store temp in head, right? So now temp is head, and there was nothing special we had to do. So that's pretty nice. So the first thing we did was, as we built this list, is that we added 1 to the list. Then we added 0 to the front of the list. Then we added -12 to the list. And then we added +5 to the list. Right? And then initially 1 was head, and 0 was the head, and -12 was the head, and then the 5 was the head. And what's cool about this is that if you're keeping track of the big O's, right, the algorithmic efficiency right now, this is a simple statement. This is a simple statement. These are simple statements that don't depend on the size of the list. So all these, so adding to the beginning, that's a constant time operation, as opposed to having to shift everything over. So now printing out everything in this list, let's go through it. Let's go and through how we got this answer over here, 5, negative 12, 0, 1. Okay? So the first thing we did is that we created a new string builder, which is just simply we're going to represent with our string. First thing we did was for our string was that we added this bracket over here, right? Created this bracket. The second thing is that we said that current is equal to head. Okay. So while current.next is not equal to null, while current.next item is right now negative 12, so it's not equal to null, we are going to append current.item and a space. So we're going to add 5, and then we're going to add in space. So I can't really write a space. Can't write nothing. And then the next thing it says current is equal to current.next, which says let's go ahead and take what's in current.next, the node current.next, and sort in current, which means just advance current. So remember, if we were looking at this like this, current was pointing to this one, and we said let's go to current.next instead. Current.next is equal to current. So now we point here. So now we do the same thing. Is current next node, which is 0, is that null? No, it's not. So we append the item with a space, and then we say current is equal to current.next. Okay, same thing. Is this next thing null? No, it is not. So we add a 0, then a space, and then we go on to, and then we advance to the next item. Is this thing's next up null?
Yeah.
It's null, correct. So we don't do this bit over here, and instead we just append the 1 followed immediately by the bracket, so we don't have that extra weird space just randomly hanging out. And then we just turn this into a string. We return this as a string to the user. Okay, so it's pretty hefty stuff right now, right? We're getting a bit down into the weeds, just jumping around with memory locations. But again, the way to remember this is that basically everything in here I'm just drawing as that they've got, the arrow is just it's easier than just like doing that, just doing like that actual scavenger hunt than where I put labels down, because the labels are super time consuming. Instead, we just basically follow the arrows everywhere, and that's the easier way to work with linked lists. That's how you see them mostly abstracted out. So now if I wanted to add something in between, what if I wanted to add something in between? Like say I've got Tom and Dick, and I want to add Ann in between Tom and Dick. Okay? Well, the same thing applies. First thing I have to do is attach Ann to where she should need to be in the list. I attach her to whatever should come after her, and then I update the list accordingly. Okay? So I'm going to draw this out over here. Say I wanted to add the number 42 between negative 12 and 0, okay? What we don't want to do is move the stuff in the list first. I don't want to attach negative 12 to 42, because while I wouldn't lose my head over here, I would lose everything that came after negative 12, right? So the first thing I need to do is attach the new node I'm adding. Over here, right? And then I can attach negative 12 to it. And now instead of going 5, negative 12, 0, 1, we go 5, negative 12, follow the arrow to 42, follow to 0, then 1. Okay. But we have a slight conundrum here, I think. A slight problem, which is that we don't necessarily know. I mean, we had adding to the head wasn't too bad because we had a reference to the head, but we have no way to you don't have a variable to reference in the middle, right? That's part of the issue right there. So instead, we'll need to write a helper method, one that we can basically get to a node, any specific node at any specific index. Okay, so let's go ahead and write that, and I think this will probably be one of the last items we write here. So public node e get node. So in previous exams on linked list, by the way, let me just tell you what the way the previous exams work, because I'm thinking I'm going to switch it up slightly. Previous exams for linked list, what I had the students do is I said you couldn't bring anything into this exam. It's closed notes, closed book, nothing into the exam. But in return, what I said is that I would tell you exactly what was on the exam. I told you exactly what 60 points of the exam would be. And then you had a pretty good idea of what another 20 of what the other 40 would be. Okay. And those three things that were on the previous exam were basically writing out verbatim what the add method was and what the remove method would be. In other words, writing verbatim what this add method was. But and while that worked as a pretty good filter, it's not. I don't know if it's because my exams just after a matter of time they eventually get leaked and shared. So I do have to change it up every so often. But what I would have you do is I write add, remove, and get node. But I will tell you, very matter-of-factly, that what will definitely be on the exam worth about 20 points is comparing and contrasting array lists to linked lists. So you at least are going to get that one for this one. And then I'll let you know later on what restrictions, if any, are going to be on the actual exam. Okay. But this other one, get node, was one of the other important ones, which doesn't get an item, right? It doesn't get something from the list. It gets a specific node. And since nodes are private, we should probably make this private. So private get node from an int index, right? We're getting a specific node from an index in the list. Okay. And what we need to do is that we want some node e. And we're going to use our current over here as well. It's equal to the head. And then return current when we're done with this. And again, part of what we want, the first thing we want to make sure, that we always want to make sure with all these methods, is that if the index is less than 0, or if index is greater than or equal to size, because size isn't a valid, size is only a valid index to add to. Throw new index out of bounds exception. Okay. Current is equal to head. We start off at the current, and then what we're going to do is that for int I is equal to 0, I is less than, and this is a bit weird, index. And I'll explain what this does in just a second. Is that this loop runs index number of times. And what it does is that it does this line, current is equal to current.next, which just simply advances current, right, in index number of times. So this line will run once if you want to go to index 1. It will run 0 times if you want to get the one at index 0. It will run 5 times if you want to get the thing at index 5. That makes sense to everybody? So let's say the input was 3, getting the thing at index 3. We'd say current is equal to head. Okay, this is my fingers at the current node. So let's say for int I is equal to 0, I is less than 3. Run current is equal to current.next, which brings us over here. Current is equal to current.next with I is equal to 1. Current equal to current.next, I is equal to 2. Then it gets updated to 3. Right? So we don't run the loop anymore. So we've advanced 1, 2, 3 times. Right? Make sense? advance 3 times. So we are at, so we return the current node. And that would be the node. It wouldn't be, remember, we're not returning 0 over here. We're returning the node that contains 0. Okay? All right. So now we have a way of getting a random node into the list. But how long is this get node operation going to take? Right? Adding to the beginning was a constant time operation. But get node, how long does this take? Yeah, O of n. It's a linear time operation because worst case scenario, we have to go through the entire list to get to the last one, or on average we go half the way through the list to get to the middle. So that's an O of n operation. So adding and removing to the linked list, as you'll see, if we're adding and removing the first thing in the linked lists or the last thing in the linked list, it always works. But right now, you're like, well, if we're removing the last thing, we have to go through the whole thing to get to the end, right? Probably thinking that. So removing from the end, it should be O of n time. Well, most of the time, we're also going to have a private node E tail as well. But I'm not going to introduce that one yet, just so we can keep this down to 3 cases, right? We have to add a 4th case, right? We have the out of bounds, we have front, and then we have everything else right now. If we add the tail, we'll have to add a 4th case. So I just want to keep it simple just while we're working on this right now. Then I'll add a 4th case later. Okay? So, adding anywhere else. So now what we need to do is that basically we've got to figure out what node we need to bother getting, right? If I wanted to add, again, if I want to add 42, if I want to add, right, this is index 0, index 1, index 2, and index 3. If I want to add 42 to index 2 to be the new index 2, right, then the question is, which one of these nodes should I get? I could get both of them, right, and just simply get half, and that's one way to do it. So let's go with the easy solution, then we'll work our way to there, okay? So let's go ahead and create a new node. We'll go with node E before is equal to get node index -1, right? Now you might be going, okay, index -1, can't that possibly fail and go out of bounds the other way? And fortunately for us, the answer is no, because it would only fail if we were at the beginning of the list, right? Index -1 would only fail if index was 0, but it can't be 0 because that's in a separate if condition. So the reason I'm doing this writing this in such a way is that it's a very protective code. The way I'm writing this helps prevent a whole lot of index out of bounds exceptions. Okay, node E after is equal to get node at the index. Okay, so we've got our before and our after. So now we can add a label to these guys, before and after, assuming I learn how to spell. Okay, so now we can attach 42 to after, right? Because the first thing we want to do is attach the new node that we just created. So the new node we have is temp. So we say temp.next. Inside of its next variable, we are going to store the memory location of after, right? Make sense? And then we say we update the list to accommodate this new reality. Before next now points to temp. That makes sense to everybody? Okay, but we can actually shorten this, right? Now, first off, you might also be asking, well, what if the index we want to add to is the last element in the list, right? Because this will work for this, right? What we do is that all we did was we attach 42 over here to after, then we attach 4 over here. But what about if we wanted to add to index, so 0, 1, 2, now this is 3, now this is 4. What if we want to add to index 5 over here? If we want to add 100 to index 5. So we've got ourselves a Well, unfortunately, our algorithm as written will currently crash, right? Because it will throw an exception. First, it will get index -1 just fine. It will get this guy at 4. Okay? But index is currently null, and if we try to do that, it's going to crash over here because that will be outside of the bounds. And we only want to get a node that exists. So fortunately, though, we have another way of referencing after. There's another way to write after, which is that it's the node that comes after before, right? So we can just simply say after is before's next, right? And if that's null, oh well, that's going to get stored in after. So now after is null, okay? So temp.next is, so temp's next is now after. This line over here says that temps.next is after. So that just simply means this points to null. That's fine. So we store null in temp.next. And then temp gets stored in, the memory location of temp gets stored in before.next. So it gets tested in list, no problem. Does that make sense to everybody? That's fairly straightforward. And if we really wanted to shorten this, which is typically the way I would do this, but I like this, now that I thought of this, this way is a really nice way to write this, is that I would typically get like, I used to write it like this. Node is equal to get node at index -1. And then I'd say temp.next is equal to node.next. And then node.next is equal to temp. So let's just simply, for the last thing in the evening, let's just simply rewrite this. So node is equal to get node at index -1. So we wanted to, so right, we're adding 100 to index 5. We say that node is this item at index, is this node at index 4, right? So we get that item. We say temp.next. The thing that temp.next is going to point to is the thing that node.next is currently pointing to. Or the way that it really happens is that we store the memory location that's represented by node.next, which is null, in temp.next. So we store null here, and then we say temp is stored in node.next. The memory location temp is stored in node.next. Yes?
It's not really temporary if it's staying in the list.
Yeah.
It's kind of
it's just a temp
name.
Oh, yeah.
Isn't it? I mean,
you are completely correct.
It's not like a variable temp where you just
right, throw it away. No, it's a temporary name was more the idea because the name is going to be thrown away after a while. So I could probably rename it now that I've come up with this naming scheme. Also, I can get that back now since I dropped it earlier. Thanks. Thanks for picking it up. But I like this naming scheme because it makes it easier to understand, even though it does use one more memory location, but that's fine. Then I'm going to keep it like this simply because because when we get to remove on next Tuesday, it will be very useful. So that's it for this lecture. So let me just go ahead and mention you do have a timed lab on this Friday, which I'm currently writing and will have done basically tomorrow, or possibly tonight when you're all gone. The idea here is that you should get, I think, you'll get 90 minutes to work on it, essentially. So you'll come in, we'll wait a bit of time for people to trickle in to make sure that there's plenty of time for it to start. And then you've got 90 minutes to complete it, and we'll give you maybe the slightest bit of like leeway when it comes to just turning it in, but we're going to be as strict as we can be with the time limit on there. Remember, your total lab is 1 hour and 20, so then you can use the remaining 20 minutes to demo whatever stuff you have. But it's going to be a bunch of separate problems that each are worth a certain amount of credit, so you can, complete a couple of them and, still pass the timed lab. And we'll see how well it works out. As far as what's allowed, honestly, this should be As far as you're allowed to bring your books and notes and use those. As far as the internet, I'm still debating with my TAs as to whether or not you can use that other than to access the assignment. But basically, it's open note and open book because those are things that you should be allowed to have. And then basically we're having a very lively debate as to whether or not you should be able to use the internet or not. And the argument is that basically that the problems are probably easy enough that you could Google. So
This Thursday.
that would be this Thursday and Friday. Okay.
It's 5%.
It is 5% of the grade, unless we need to adjust the actual amounts for some reason.
Just a quick